It is necessary to ground the power supply of a dental chair in a solidly grounded system. NEC 250.4 A5 requires that all electrical equipment and metal raceways be grounded in solidly grounded systems. This includes dental chairs, which are electrical equipment that must be connected to a grounding electrode system. Grounding provides a lower resistance path for fault currents to flow back to the source, preventing dangerous voltage buildup. In the case of a dental chair, grounding helps to protect patients and personnel from electrical shocks and other hazards. The power supply of the dental chair should be grounded using an equipment grounding conductor, often referred to as EGC. The EGC is a bare or insulated copper wire that connects the equipment to the grounding electrode system. The EGC should be sized in accordance with NEC requirements. Once the dental chair is grounded, it is important to verify that the grounding system is functioning properly. This can be done using a ground resistance tester or by measuring the ground fault impedance. While the NEC does not specifically mention dental chairs in section 250.4 A5, it does require that all electrical equipment be grounded. Dental chairs fall under the category of electrical equipment and, therefore, must be grounded in a solidly grounded system. Let's delve into the specifics of grounding electrical equipment, especially in the context of a dental chair within a solidly grounded system. Grounding in electrical engineering serves as a critical safety measure. Its primary purpose is to provide a low impedance path for fault currents to return to the source. This action prevents hazardous voltage buildup on equipment enclosures and other conductive surfaces. In a solidly grounded system, the neutral point of the power source, typically a transformer, is directly connected to the earth. This connection creates a low resistance path that facilitates the rapid clearing of ground faults. Now, considering a dental chair, which contains electrical components and metal parts that could potentially become energized due to insulation failure or other faults, grounding becomes paramount. Should a fault occur, the grounding system ensures that the fault current flows back to the source, tripping a circuit breaker or fuse and energizing the circuit. This action minimizes the risk of electrical shock to patients and dental personnel who might come into contact with the chair. The NEC, or National Electrical Code, provides comprehensive guidelines for electrical installations, including grounding requirements. While the code might not explicitly mention dental chairs, its general provisions for electrical equipment apply. Section 250 covers grounding and bonding, detailing the methods and requirements for establishing a safe and effective grounding system. NEC 250.4 A5, as mentioned, emphasizes the need to ground all electrical equipment. This requirement extends to any device that utilizes electricity and has the potential to pose a shock hazard. A dental chair certainly falls under this category. To properly ground a dental chair, an equipment grounding conductor (EG) must be installed. The EGC is typically a copper wire, either bare or insulated, that runs along with the circuit conductors supplying power to the chair. This conductor connects the metal frame and other conductive parts of the chair to the building's grounding electrode system. The grounding electrode system usually consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes that are buried in the earth and connected together to form a low impedance path to ground. The size of the EGC is determined by the size of the circuit conductor supplying the dental chair. NEC Table 250.122 provides guidance on selecting the appropriate EGC size based on the overcurrent protection device, such as a circuit breaker or fuse, protecting the circuit. For example, if the dental chair is supplied by a 20 amp circuit, the EGC would typically be a number 12 American wire gauge or AUG copper wire. When installing the EGC, it is crucial to ensure that all connections are mechanically sound and electrically conductive. This means using appropriate connectors such as grounding lugs or crimp connectors and tightening them securely. All connections must be free of corrosion and other contaminants that could impede the flow of current. Furthermore, the EGC must be continuous and unbroken from the dental chair to the grounding electrode system. Splices are generally not permitted in EGC, as they can introduce resistance and compromise the effectiveness of the grounding system. After the dental chair has been grounded, it is essential to verify that the grounding system is functioning correctly. This can be accomplished using a ground resistance tester or by measuring the ground fault loop impedance. A ground resistance tester injects a small current into the grounding system and measures the resulting voltage drop. This measurement allows you to calculate the resistance of the grounding path. A low resistance value, typically less than 5 ohms, indicates a good grounding connection. Ground fault loop impedance measurement involves determining the total impedance of the path that a ground fault current would follow from the point of the fault back to the source. A low impedance value ensures that a fault current will be high enough to quickly trip the overcurrent protection device. In addition to the EGC, other measures can be taken to enhance the safety of the dental chair. Firstly, ensure that the chair is plugged into a properly grounded receptacle. The receptacle should be tested to verify that the grounding pin is connected to the building's grounding system. Secondly, consider using a ground fault circuit interrupter, or GFCI, to protect the circuit supplying the dental chair. A GFCI is a device that monitors the current flowing in the circuit and detects any imbalance between the hot and neutral conductors. If a ground fault occurs, even a small one, the GFCI will trip the circuit, cutting off power and preventing electrical shock. GFCIs are particularly useful in healthcare settings, where patients may be more vulnerable to electrical hazards. Thirdly, regularly inspect the dental chair and its power cord for any signs of damage, such as frayed wires or cracked insulation. Damaged cords should be replaced immediately. Also, make sure that the chair is properly maintained and that any electrical repairs are performed by a qualified electrician. To summarize, grounding the power supply of a dental chair in a solidly grounded system is a necessary safety measure mandated by the NEC. Grounding provides a low impedance path for fault currents, protecting patients and personnel from electrical shock. To properly ground a dental chair, install an equipment grounding conductor EG, sized according to NEC requirements. Verify the effectiveness of the grounding system using a ground resistance tester or ground fault loop impedance measurement. In addition to grounding, other safety measures such as using GFCIs and regularly inspecting the equipment can further reduce the risk of electrical hazards. Let's further clarify the concept of solidly grounded systems and their importance in electrical safety. A solidly grounded system, also known as a directly grounded system, is an electrical distribution system where the neutral point of the source transformer or generator is directly connected to the earth. This connection is typically made at the service entrance of a building. The primary advantage of a solidly grounded system is its ability to quickly clear ground faults. When a ground fault occurs, a large fault current flows through the low impedance path created by the grounded neutral. This high current causes the overcurrent protection device, such as a circuit breaker or fuse, to trip rapidly, disconnecting the faulted circuit and minimizing the duration of the fault. The rapid clearing of ground faults is crucial for preventing electrical shock and minimizing damage to equipment. In contrast to solidly grounded systems, there are other types of grounding systems, such as impedance-grounded systems and ungrounded systems. Impedance-grounded systems use a resistor or reactor to limit the ground fault current. Ungrounded systems, as the name suggests, do not have a direct connection to ground. While these systems may offer certain advantages in specific applications, they are generally not recommended for most commercial and industrial installations due to their increased risk of overvoltages and difficulty in detecting ground faults. Solidly grounded systems are the most common type of grounding system used in North America and are required by the NEC for many applications. The NEC provides detailed requirements for grounding and bonding in solidly grounded systems, covering topics such as grounding electrode systems, equipment grounding conductors, and bonding of metal parts. Now let's elaborate on the specific requirements for grounding electrical equipment in solidly grounded systems, as outlined in NEC 250.4. F5. This section of the NEC mandates that all electrical equipment that is likely to become energized be grounded. This includes equipment such as motors, appliances, lighting fixtures, and, of course, dental chairs. The purpose of grounding electrical equipment is to provide a low impedance path for fault currents, as previously discussed. However, there are some exceptions to the general requirement for grounding electrical equipment. One exception is for double insulated equipment. Double insulated equipment is designed with 2 layers of insulation, eliminating the need for grounding. The outer layer of insulation provides an additional layer of protection against electrical shock. Double insulated equipment is typically identified by a symbol consisting of a square within a square. Another exception is for equipment that is supplied by a low voltage circuit and is not likely to become energized. However, this exception is rarely applicable in healthcare settings where the risk of electrical shock is higher. When grounding electrical equipment, it is crucial to use the appropriate type and size of equipment grounding conductor. The EGC must be sized in accordance with NEC Table 250.122 based on the overcurrent protection device protecting the circuit. The EGC must also be installed in a manner that ensures a continuous and low impedance path to ground. This means avoiding sharp bends, splices, and other discontinuities that could increase the impedance of the grounding path. In addition to the EGC, other measures can be taken to improve the effectiveness of the grounding system. One measure is to bond together all metal parts that are likely to become energized. This includes metal raceways, enclosures, and other conductive surfaces. Bonding ensures that all metal parts are at the same potential, reducing the risk of electrical shock. Another measure is to use a supplemental grounding electrode. A supplemental grounding electrode is an additional grounding electrode that is installed to improve the overall performance of the grounding system. Supplemental grounding electrodes are particularly useful in areas with poor soil conductivity. Now, let's focus on the practical aspects of grounding a dental chair in a healthcare facility. The first step is to identify the source of power for the dental chair. This is typically a branch circuit that originates from a panel board in the electrical room. The next step is to determine the size of the circuit conductors and the overcurrent protection device protecting the circuit. This information can be found on the panel board schedule. Once the size of the circuit conductors is known, the appropriate size of the EGC can be determined using NEC Table 250.122. The EGC should be run along with the circuit conductors from the panel board to the dental chair. The EGC should be connected to the metal frame of the dental chair using a grounding lug or other approved connector. The connection should be mechanically sound and electrically conductive. The EGC should also be connected to the grounding electrode system in the electrical room. This connection can be made to a grounding busbar or to a grounding electrode conductor. Once the dental chair has been grounded, it is important to verify that the grounding system is functioning correctly. This can be done using a ground resistance tester or by measuring the ground fault loop impedance, as previously discussed. If the grounding system is not functioning correctly, the problem should be identified and corrected. Common problems include loose connections, corroded connections, and undersized grounding conductors. In addition to the grounding requirements outlined in the NEC, healthcare facilities may also be subject to additional grounding requirements imposed by other regulatory agencies, such as the Joint Commission. These requirements may be more stringent than the NEC requirements and should be carefully followed. It is also important to note that the grounding requirements for dental chairs may vary depending on the specific type of chair and the environment in which it is used. For example, dental chairs used in wet locations may require additional grounding protection. Therefore, it is essential to consult with a qualified electrician to ensure that the dental chair is properly grounded in accordance with all applicable codes and standards. By following these guidelines, healthcare facilities can ensure the safety of their patients and personnel and minimize the risk of electrical shock. Let's consider some additional factors that can influence the effectiveness of a grounding system. Firstly, the soil resistivity plays a significant role. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity allows for better grounding performance. Factors such as soil composition, moisture content, and temperature can affect soil resistivity. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes with chemical treatments to improve grounding performance. Secondly, the length of the grounding conductors can impact the overall impedance of the grounding path. Longer conductors have higher impedance due to their increased resistance and inductance. Therefore, it is important to keep grounding conductors as short as possible. Thirdly, the presence of electromagnetic interference, or ME, can affect the performance of a grounding system. EMI can induce currents in grounding conductors, which can degrade the effectiveness of the grounding system and potentially cause equipment malfunction. To mitigate EMI, it may be necessary to use shielded cables or install filters on the grounding conductors. In addition to these factors, the overall design of the electrical system can also impact the effectiveness of the grounding system. A well-designed electrical system will minimize the potential for ground faults and provide a lower impedance path for fault currents. This includes using properly sized conductors, installing adequate overcurrent protection devices, and bonding all metal parts. Furthermore, regular maintenance and inspection of the grounding system are essential for ensuring its continued effectiveness. Grounding connections should be checked for tightness and corrosion, and grounding conductors should be inspected for damage. Ground resistance measurement should be performed periodically to verify that the grounding system is still functioning properly. In summary, grounding dental chairs, as with all electrical equipment, is not just about meeting code requirements. It is about ensuring a safe environment for patients and dental personnel. By understanding the principles of grounding, following the NEC guidelines, and taking into account the factors that can influence grounding performance, healthcare facilities can create a safe and reliable electrical system. The information provided serves as a general guide and should not be considered a substitute for professional advice from a qualified electrician or engineer. Always consult with a qualified professional before making any changes to an electrical system.